This is the last section of this section, and it talks about pressure changes, volume changes, temperature changes, as well as the effect of a catalyst. So let's attack volume pressure first. I kept it in the same order as your textbook goes. Think back to chapter 10. If you're going to increase the pressure on, let's say, a cylinder, if I have a cylinder and there's a piston sitting here, and I increase the pressure, what will happen is that piston is going to move down. We're going to see the volume decrease. The corollary is as the pressure decreases, the volume is going to increase. Think of the piston going up. And I always wonder why they don't mention a piston, because just trying to think about it, you need something real. So this is the old nitrogen dioxide, which is orange, brown in color. And none of you football fans know the Cleveland Browns are playing. And what will happen is it can go in equilibrium with dinitrogen tetraoxide, which is colorless. So what's going to happen if the pressure is increased? Well, we have two gas molecules on the left. We have one gas molecule on the right. What will happen is the stress will be reduced by reducing the number of gas molecules. And I say gas. So if I have 2 versus 1, I am going to go to that 1, and my reaction is going to shift to the right. So all you need to do is count, and count only the gas molecules when we're looking at a pressure effect. Try your homework. It's going to help you learn this. If there's the same number of gases on each side of the equation, you're simply not going to see any shift. If you pump in an inert gas, and what do we mean by that? We mean the gas is not in the equation. We will also see no effect whatsoever. And if you have a solid or a liquid, you also have no effects. So this really involves gases only. This is called the effect of volume pressure changes. The next one is the temperature that was alluded to in the earlier video. So I can change my concentration, I can change my pressure, and there's no effect at all on K. But if I change the temperature, I'm going to have a change in K. It will be a new value, okay? So let's talk about the two kinds of reactions that you learned about in 1210. If we have an endothermic reaction, heat is a reactant. Write it down in the equation. It'll always give you the right answer. If I add the heat, I'm putting stress on the left side. My reaction is going to shift to the right until equilibrium has been restored. Again, this is only with temperature. Products divided by reactants. I will have more products, I will have less reactant. So what will happen is my K value is going to increase. If this is brand new to you, just think of this first example. Know your endo example perfectly. That way, if you are faced with an exo example, you'll know it's not endo. And what I did here, I know I'm being silly, is I put a little heart around the heat because heat for an exothermic process is a product. If I'm going to add heat, I'm going to stress that stress the right side, and the reaction is going to shift to the left until equilibrium is restored. So more reactants have formed. If I look at my expression for K, products over reactants, there is less product and there is more reactant. So my K value is going to decrease. You notice I had trouble saying it. So please write it down as you solve a problem, and chances are you're going to come up with the right answer. Okay. So let's take a couple examples. Let's say I have sodium carbonate. Sodium bicarbonate goes to form sodium carbonate and CO2 and water. What happens if I increase the pressure? Well, I have 0 gases on the left. I have 2 gases on the right. If I increase the pressure, I am going to shift to the left. Practice these. How about if I have my NO2 gas and my N2O gas? I can say to you, okay, what's going to happen here? We've said the NO2, oh, and someone didn't balance this equation. Oop, there are two of them. I can't seem to write the number in here. Okay, be that way. There are two of them. Got to kind of go back to put my little things in. There are two NO2s and one N2O4. This is orange-brown, like the Cleveland Browns, and N2O4 is colorless, okay? It says if I add heat, it turns orange-brown. So what way did the shift go? Well, if I shifted to the left, that would give me the orange-brown color. That means if I added heat, heat had to be sitting as a product, and that says this has to be an exo reaction. You're using all the things you taught yourself back in Chemistry 1210, and we're just building upon it. We don't expect you to do these calculations anymore, but there is yet another relationship where there are 5 different variables, and if you're given 4 of them, you can find the 5th one, and this is the same delta H from chapter 5, okay? What's left in this section? Well, I like to always end this with an example. If I want to do all these 4 different things here on the left, what's going to happen to my shift? What's going to happen to my amount of CO? What's going to happen to my K? I could write all these things in, but then you just look at them. So I'm going to say, please come to the lecture Zoom and we shall work it out. It's got a couple twists and turns because we have solids, we have different amounts of gases, we have some heat energy involved, and it is an endo reaction. So try to work it on your own. Come to lecture Zoom and we'll do it together. Last part is, what happens when you have a catalyst present? Well, we know a catalyst gives you a new path. We know the catalyst is going to lower the barrier between the reactants and products. What it does is it's going to increase the rate of both the forward and the reverse reaction. It does not change the composition of the equilibrium mixture. You will still have the same K. Again, this wraps up our chapter on equilibrium, which taught you what is an equilibrium constant, products over reactants. In the middle, we learned how to calculate a K. We learned how to calculate concentrations. We learned how to use the variable X, and we wrap things up with LeChatlier. I call this an easy chapter. Please don't move on to acid-base chemistry until you really have a good grip on this, because acid-base chemistry uses equilibrium.